I was asked for an example of another related rates problem that you could get some practice with. So I posted it through on campus, but I also want to show you a solution so that as you're working for it, you can see whether you might be able to do a problem like this. The unique thing about this problem is it can be done with two completely separate approaches. One is kind of elegant, you might not think of. I'm going to show you that one first, but I want to reassure you that there's kind of a brute force way to go about this problem. So you've got this beacon, basically a lighthouse out here, and this beam of light is being shot out from it, and so it's coming like this, and it's just rotating around as a beam of light would coming out from a lighthouse. And if you've ever watched that coming out, it kind of seems to go around kind of slowly, and then when it comes by the shoreline, it's going to kind of whip kind of quickly because this thing is really far out. It's like the difference between when you're on a carousel and you're in the middle, you're not covering very much distance as you're moving around because the circle that you're sweeping out is kind of small. If you go out to the end of toward the edge of a carousel, even though you're, say, rotating one time every 3 seconds, if I make it around in 3 seconds, 1001, 1002, 1003, think about how far we went there compared to how far we went here. You're going to get a lot of linear speed. You're going to cover a lot of feet every second. So one way to do this is we were given some information about how far it is, 3,600 feet out. The beacon turns at 4 pi radians every minute. That's basically twice, well, it's not basically, it's exactly 2 times around every minute. And the question is, how fast is this beam of light sweeping by the shoreline when it gets right there at that instant where point P is? The elegant way to think about this is think about a big circle and think about this arc length right here, the length of that arc, and how that length is changing at that instant. So for that, we would need the formula for arc length. And this is why I said this is kind of an elegant solution I think not many students would think about. But arc length is usually used S equals, and it's just r theta. Now, that's as long as the angle is measured in radians. So there's a relationship. Now in this case, r is not changing. The radius of this circle is constant at 3,600. So you get S equals 3,600 theta. And that's always going to be true. The arc length is always going to be 3,600 feet times whatever the angle is. So the rate of change with respect to time, so that the rate at which this arc length is changing as it moves, say, from here to here, is going to be dependent upon the rate that the angle is changing. So by the time this angle gets down to being horizontal, where that angle right in there is essentially going to be 0 radians, how fast is this arc length shrinking? Say the arc from here to here. How fast is it shrinking at the instant it gets to 0 radians? So all we have to do is take the derivative with respect to time. So we're going to say ds dt equals 3,600 d theta dt. Very easy derivative to take. ds dt is what we're looking for. That's our question. And we know that d theta dt is given to be 4 pi radians every minute. So 3,600 feet times 4 pi, and that's going to be in feet per minute. And so that's basically the answer. You're not going to have a calculator on a test like this, but the numbers would work out such that you could figure out a problem. But essentially, that's the answer. That's not essentially, that is the answer. Another way to think about this problem is just to kind of take this beam of light and extend it right out to the shoreline here so that it's thinking like that. And then as this angle is coming down here, think about the rate at which this opposite side of this triangle is getting shorter and shorter and shorter. So as this beam's shooting out here, this thing is going to be coming down and getting shorter. So we could think about the length of that side. You could call that, I don't know, y or something like that. This is 3,600 there, and then we've got theta here. So you think about something that's always going to be true in this triangle, and it's going to be that the tangent of theta is y over 3600. So you can do this problem this way and say tan theta equals y over 3600. Multiply both sides by 3600 and get y equals 3600 tan theta. And now what essentially we're looking for is dy dt. You're saying how fast is this side shrinking at the instant when the angle again is 0 radians. So we can say that dy dt is equal to the derivative of 3600 tangent theta, which is a constant times the function. So the derivative is the constant times the derivative of the function. And the derivative of tangent is secant squared. So let's see if we can get that going on there. Secant squared theta. Now we got to use the chain rule, d theta dt. And so we have, at this instant, we have theta equals 0 radians. So we're going to plug that in there. And of course, the secant is the reciprocal of the cosine. So the secant squared is the reciprocal of cosine squared. So we're talking about 1 over the cosine squared of 0, which is 1 over the cosine of 0, which is 1 squared. So it's 1 over 1 squared, which is 1. So we get 3600 times 1 times d theta dt, which of course is that 4 pi. And so you get feet per minute again. So it's 3600 times 4 pi. Now, just taking a look at the units up here, they wanted feet per second. So we'd have to convert feet per minute into feet per second. So we just say in 1 minute, we have 60 seconds. So we can now, to go ahead and get the full solution, 6 goes into 36 6 times. So we can cancel this 0 with that 0, and then 6 goes into 360 60 times. So it's like 60 times 4 pi feet per second. So 240 pi feet every second. There's our solution. So again, 2 different approaches to it, but as you can see, you get the exact same answer both ways. That's a cooler problem and how you have to think about it. But again, the key is trying to get the relationship that's always true, regardless of which situation we're talking about. If we think about the right triangle setup here, the tangent of theta is always going to be y over 3600. If we think about this more elegant solution of this arc length changing as that circle gets, as this sector rather gets smaller and smaller, you could think of this way. But it's kind of cool how they both give the same solution. Both give the same correct solution. So there you go.